Okay, hello. Welcome to lesson 2 of the stoichiometry unit. Hope lesson 1 went well for you. We're going to cover a couple more things in this unit. What we're going to talk about today, two main things that I want to talk about are the mole, not the cute fuzzy animal. It's actually a number. We'll talk about that. And then the other thing we're going to talk about is a little something I like to call dimensional analysis. Okay, in this unit, we're talking about chemical equations. Both of these topics have to do with that. So let's go ahead and get started with talking about the mole. Okay, so in talking about the mole, really what this is this is a number that is extremely common in chemistry. I'll tell you what that number is specifically here in a moment, but before I do, I kind of want to give a context for what this is before we actually get there. So basically, the mole is a word that represents a certain number, okay? And you guys are already familiar with this concept, okay? So let me kind of give some examples to give an idea of what we're talking about, okay? So if I throw out a word like single, that is a word that represents a certain number, right? If I say I have a single calculator here, that means that I have one calculator, okay? Now I'm going somewhere with this, okay? Don't roll your eyes too quickly. If I say something like I have a couple markers here, right? We know that this word means I have two markers, right? Similar words that kind of fall into this category. Dozen. If I say I have a dozen of something, we know that is the same as saying 12. Okay, some bigger ones, we don't use these very commonly, but you guys may have heard of a score, fourscore, and so many years ago, I can't even remember that speech, sorry about that. That's why this is chemistry class. Okay, but anyway, score. So score is 20, right? If I have a score of, I don't know, soldiers, then I have 20 soldiers in my platoon or whatever that group is. A score. Some other things. Grand. This is a more common word with money. If I have a grand, that's another word for 1,000. Okay. So a mole is a word that represents a huge number. Okay. How huge exactly? Well, here, let me just write down this number. 6.022 times 10 to the 23rd power. Okay, so I have 6.022 times 10 to the 23rd power. Okay, so going from 1,000 to this number is a huge jump, but I'm just trying to make an example of we have certain words that represent certain numbers, okay? Now, a mole is absolutely huge. If I were to write this out in decimal form, right, multiplying times 10 to the 23rd means I would move the decimal place 23 times over here. And so we're talking about millions of millions of millions of millions of millions, right? For example, I don't know, if I had a mole of peas, like the little vegetable, that would cover the entire surface of the earth very deeply. So this is a huge number. Okay, so why is this number important? What does this number have anything to do with chemistry? Okay, well, the reason this is important is because when we're talking about chemical equations, right? Let me pull up an equation we talked about in the last lesson. Nitrogen equals this, and then we needed to balance it, so 2 and then 3, right? Balanced, so I've got nitrogen plus hydrogen gives me ammonia. Okay, so the reason the mole is important is because this has to do with the mass of certain substances, sorry, didn't say that very clearly. Okay, so there's my number. Now, if we're doing this reaction, right, this reaction, when we look at it, so far, we're talking about one molecule of nitrogen gas 3 molecules of hydrogen gives us 2 molecules of ammonia. Now, if we were going to do this reaction in real life, there's no way that we could do this with a single molecule of nitrogen, 3 of this and 2 of that. That's so microscopic that there's no way we could even begin to do that reaction. Typically, we want to do reactions in a kind of more macroscopic unit, such as pounds or grams. Grams is really what we're going to use for the most part, because that's an international unit, right? If I have so many grams of a certain amount of substance and I want to react it with a certain number of grams of another substance, I want to know how many grams of the other product I get. Well, what we need to do is we want to be able to talk about chemical reactions in a unit of mass that is meaningful to us, such as grams, okay? And so the key to getting there from molecules to grams is going to be the mole, okay? So the mole is going to be our key there. So let me explain what I mean by that, okay? So let's talk about a carbon atom. So I'm going to put C here. If we look at our periodic table, we know that the average atomic mass for one atom of carbon, I'll put the whole word here, is 12.01 atomic mass units. Okay, so this is the average mass for one atom of carbon. Okay, now again, that's all nice and everything, but if we're doing a chemical reaction, we want to think of carbon's mass in grams. So what we want to do is we want to think of a certain number of atoms. How many atoms does it take to get us onto the scale of grams when we're doing a chemical reaction? Okay, so it turns out that, well, we have 12.01 atomic mass units. How many atoms of carbon would I need to have 12.01 grams of carbon, right? If I have one atom, I know the mass of that atom is 1 atomic mass unit. So now the question is, how many atoms do I need to get 12.01 grams of carbon? Well, turns out the answer is a mole. If I have 6.022 times 10 to the 23rd atoms of carbon, the mass of all those atoms, 6.022 times 10 to the 23, is going to be 12.01 grams. Okay, and so that's where the number of a mole comes in. Is a mole is the number of atoms that I need to turn the atomic mass of an element into grams. Okay, let's do another one as an example to kind of wrap our mind around this. Okay, so that was a mole for carbon. Let's think about another element. Let's do chlorine. Okay, if I look at my periodic table, I see that the average atomic mass for a chlorine atom is 35.45 atomic mass units. Okay, and I know that I have one atom is going to give me that mass. Okay, and then if I'm doing a chemical reaction, I want to think about this in grams. So I might ask myself, how many atoms of chlorine will I need to get me from 35.45 atomic mass units all the way up to 35.45 grams of chlorine? Well, it turns out, just like carbon, if I have the same number of atoms, 6.022 times 10 to the 23 of chlorine, the mass of all of those atoms together is 35.45 grams of chlorine. Okay, so the mole we can see is the key to getting mass of a certain element into grams and talking about it in that way. It helps us convert from AMU to grams. Okay, let's just do another one just to make sure we really understand what's going on. If I think of another element, I'm going to pick lead. Here's the symbol, Pb, lead, right? If I look at my periodic table, it tells me that one atom of lead is 207.2 atomic mass units. Okay, I'm going to make a note, that's one atom. Let me ask this backwards. So let me say this. If I have 6.022 times 10 to the 23 atoms of lead, if I had this number of atoms, what mass would all of those atoms put together be? Well, you probably guessed it right. The mass of this number of atoms of this element is simply the atomic mass unit in grams. So if I had a mole of lead atoms, the mass of all those atoms would be 207.2 grams of lead. Okay, so the mole is very important because it allows us to talk about elements, the mass of elements, in a scale that we can make sense of on a macroscopic level when we're doing actual chemical reactions. Like, like we said before, we have other words that we could use. We could use couples of atoms or dozens of atoms. Or grands, in thousands, but those numbers are pretty small compared to how many atoms we need to get on the gram scale. To get on the gram scale, we need to talk about moles of atoms. And so the mole is a number I would encourage you to memorize. It's not too bad, 6.022 times 10 to the 23. That is kind of the grouping that we use to talk about mass of elements in chemical reactions. Okay, and so what that leads us to is this idea of, so let me go back to so we had this reaction. Nitrogen plus hydrogen yields ammonia. So before, when we were doing this, we thought of this as one molecule of nitrogen plus 3 molecules of hydrogen gives us 2 molecules of ammonia. Well, with our new concept of the mole, we can now think of this in units of moles, right? If I had 1 of these and 3 of these and 2, I'm sorry, let me back up. If I had 1 of these and 3 of these, I get 2 of these, right? If I had 1 dozen nitrogen molecules and then 3 dozen hydrogen molecules, I would get 2 dozen ammonia molecules, right? So the unit is the same with the coefficients, right? If I use singles or dozens, or if I use moles, if I had 1 mole of these molecules and 3 moles of hydrogen molecules, I would get 2 moles of ammonia. Okay, so a mole then is how we talk about chemical reactions, right? Instead of thinking of it as small numbers of molecules, we think of it in terms of moles. That's kind of the unit that we use. And again, it doesn't change the coefficients. The ratio is still the same, but we're just thinking of it in groupings of mole. Okay, so that is where the mole comes in when we talk about chemical reactions. Okay, which then leads us to an idea of molar mass. And really what this is, let me write this out. A molar mass of an element is a mass obtained from having 6.022 times 10 to the 23 atoms of a certain element. Oh, actually, it also works for molecules. Molecules. I'll say substance. Okay, so let's think about this. If I had a mole of carbon atoms, I want to know how many grams is that? Well, we talked about before, if I have a mole of a certain element, the mass of that collection in grams is the exact same as the mass, is the same number as the atomic mass unit for one atom, right? One carbon atom weighs 12.01 atomic mass units. And so, because of the mole, if I have that number of carbon atoms, the mass of that collection is the same number in grams, right? If I had 6.022 times 10 to the 23 of chlorine atoms, I know that one chlorine atom is 35.45 atomic mass units. So so that's one atom. I know that if I have 6.022 times 10 to the 23 chlorine atoms, the mass of that collection, again, is 35.45 grams. So this number here, and then from before for carbon, these numbers are what is known as the molar mass of these elements. Okay, so if I want to determine the molar mass of an element, all I need to do then is go to the periodic table, look at the mass that's given for that element, and if I put grams after it, that is the mass of having 1 mole of that element, whatever element I'm talking about. And so the way we typically write it is we say a certain number of grams per mole. Right? So the molar mass of chlorine would be 35.45 grams per mole of chlorine atoms. Okay. One other thing real quickly is I also said this works for molecules. Right? So let's think about water. Let's think about a water molecule. Well, if I had one molecule of water, and I wanted to know how much that weighed in atomic mass units, I would just need to add up 2 hydrogens and 1 oxygen, right? That would give me the mass of 1 molecule, right? If I happen to know that, we'll just say hydrogen is 1 atomic mass unit, so there's 2 of those, and then oxygen is 16. So then the mass of 1 molecule of water is going to be 18 atomic mass units if I add all this together, 2 hydrogens and 1 oxygen. The same idea with mole applies to molecules. What if I had 6.022 times 10 to the 23 molecules of water? What would the mass of that collection be in grams? Well, it's the exact same number as that mass there, except it's in grams now. So we have 18 grams. So 18 grams per mole of water molecules is the molar mass of that compound. And that'll work for any compound that you may run across. The molar mass applies to single elements and molecules as well. Okay, so we've covered the mole. We have an idea for what that is. Now we want to talk about something called dimensional analysis. Okay, and really what this topic is what this means is converting units. Okay, and just a moment ago we talked about moles and grams and how we can think of the mass of different chemicals in these different terms. Sometimes it'll be useful to convert between those two units. Okay, now in converting between these two units, we're going to use a special technique where we use something called conversion factors. Okay, and what I want to do first is I want to talk about how to use this technique, and then we're going to apply it to this idea of the mole. Okay, so before we get there, let's talk about what a conversion factor is and how we use it. Okay, so what a conversion factor is, let's define it real quick. And the way I'm going to define it is a ratio of equivalence for two different units. Okay, so what this means is a ratio. Okay, so a ratio means I'm going to have a fraction. Okay, and I'm going to have two different units that I'm going to convert between. Okay, so for example, let's pick two units of time, let's say. So let's say I have seconds, and I want to convert a certain number of seconds to minutes. Okay, now depending on the case, this may be something you could do in your head, and you wouldn't necessarily need some sort of factor to do it, but just for the sake of learning this technique, let's do this. So basically what we want to do is we want to set up our ratio where we have one unit on top and one unit on the bottom. And what we're going to do is we're just going to put the ratio of numbers that make these units equivalent, right? A ratio of equivalence, right? And so basically what I need to ask is, how many seconds are in a minute? Well, there are 60 seconds in 1 minute, okay? And so this is going to be my conversion factor. And so what this will allow me to do is that, let's say I wanted to convert 107 seconds, and I wanted to figure out how many minutes that was. Well, I know that it's probably going to be greater than 1 minute, because 1 minute is 60 seconds, and it's a little bigger than that. But it's not quite 2 minutes, because I know that 2 minutes is 120 seconds. It's somewhere in between there. But with this kind of weird number, it's kind of hard to figure it out specifically. So that's where our conversion factor is going to come into play. Okay, so the way I'm going to do this is I'm going to take my starting number, and what I want to do is multiply it by my conversion factor to get my answer. Okay, now before I write this in here, I'm going to use this conversion factor, but what I can do is I can actually flip this conversion factor either way I want, right? So I can say 60 seconds per minute, or I can say that there is 1 minute per 60 seconds. Okay, so conversion factors can be flipped up either way, depending on how we want to use it, okay? And so what we want to do is we want to set up our conversion factor so that my units that I'm trying to get rid of will cancel out, okay? I have seconds here, and I want to cancel that out with seconds down here so that I'm left with minutes, right? Because that's what I'm trying to solve for. Okay, so figuring out which direction this goes is important, okay? So I'm going to use this conversion factor to solve this problem. Okay, so now it just becomes simple arithmetic to solve this. So I'm going to have 107 seconds times 1 minute divided by 60 seconds, right? And my seconds will cancel out, and I'm going to be left with 107 divided by 60 minutes. Okay, so let me grab my calculator here and figure that out real quick. I'm going to do 107 divided by 60. I don't think you can really see the screen. If I do that, I'm going to approximate this. I'm going to get 1.78 minutes. Okay, so my conversion factor, when I set it up in such a way where the units will cancel out, will help me determine the number of new units that I'm trying to figure out, right? So if I have 107 seconds, I can use my conversion factor to determine how many minutes I have, okay? So that's an example of how that will work, okay? Let's practice this one more time with some different units, and then we'll get back to moles here in a second, okay? But I want to practice this technique before we get too far ahead of ourselves, okay? Let's jump straight to a longer one. So let's do another unit of time. Let's say I have 1.7 years. I'm going to abbreviate that like that. And I want to convert my unit into minutes. Okay, so I have a length of time, 1.7 years, and I want to figure out how many minutes are in that length of time. Okay, now with a conversion factor, it would be kind of nice to figure out, okay, well, how many minutes are in a year? Well, I don't know that off the top of my head. Some of you might, and I would be very impressed if you knew that. But this is not a conversion factor that I can make off the top of my head. But what we can actually do is we can use several conversion factors in a row to figure this out, right? I know how many minutes are in an hour. And I know how many hours are in a day. And I know how many days are in a year. And so if I use these three conversion factors, I can convert years to minutes using this progression here. Okay, so let me fill in these numbers. Minutes in an hour, there are 60 minutes in 1 hour. There are 24 hours in 1 day. And there are 365 days in 1 year. Okay. Okay, I'm not multiplying this right now, I'm just writing them all out next to each other. Okay, so in my conversion, what we always do, we start with our first number, and then what I'm going to do is I'm going to set up my conversion factors so that I end up with the unit that I want. Okay, I have 3 conversion factors, and I know I'm going to use all 3 of them. Right? So our first step is I need to convert years into days. Right? So that's going to be this one, right? So I'm going to use this conversion factor, and then I need to ask myself, do I plug it in as is, or do I need to flip it over? Well, I want to cancel out years, so I want years to be down here, and I want days to be up here, because in this first conversion I'm converting to days. So that's actually written in this way, so I'm going to just leave it as it is, like that. So that way my years will cancel out. So that'll convert me to days. Then I want to convert to my days to hours, right? So I want my days to cancel out here with here, so my hours will be on top, and I've got 24 hours in a day. And then I'll be in hours, and I want to convert those hours to minutes. So I'm going to put minutes on top here and have hours on bottom to cancel out, right? And so now it's just a matter of multiplying all these fractions, right? And I can see, based on how I've set it up, years is going to cancel out with years, days cancels out with days, hours cancels out with hours, and I'm just left with minutes. Okay, so that's how my conversion is going to work. So now I just need to multiply everything. I'm going to take 1.7 times 365 times 24 times 60, and then technically it's divided by 1, divided by 1, divided by 1, but we know that dividing by 1 won't change the answer. So what I just need to do is multiply all of these numbers together. I'm going to write it out just so you can see what I'm doing. Like that. So let me grab my calculator. 1.7 times 365 times 24 times 60 is going to give me 893,520 minutes. Okay, and so this is our technique of converting different units. Okay. So again, this technique is important. Now let's think about, what if I had a certain number of grams? Well, actually, let me do moles. Okay, so we've talked about the technique of conversion factors. Now let's relate it back to moles. Okay, let's tie this together. So we've talked about the idea of moles and grams. And we want to think about, how can I convert between these two units? So let's just say I have some carbon atoms. Don't ask me where I got them. I just happen to have some carbon on hand. And I have 3.7 grams of carbon. And I want to know how many moles, right? Remember, a mole is just a unit of this, 6.022 times 10 to the 23. I want to know how many moles are in 3.7 grams of carbon, right? You may recall from earlier, if I had 12.01 grams of carbon, that would be 1 mole, right? But in this case, I have 3.7, which is less than 1 mole. So I'm going to have some fraction of moles of carbon, but I don't know exactly how much I'm going to have, right? So in order to convert from grams to moles, I need a conversion factor, okay? And that conversion factor is the molar mass. Okay, that's the key. So recall, we talked about this earlier, the molar mass is the mass of carbon that I have when I have 1 mole of carbon atoms, right? We know that, I'm going to write it over here, molar mass for carbon is 12.01 grams, I'll just put G, per mole of carbon. So then this becomes my conversion factor. So I'm going to take this here, 3.7 grams, and if I multiply it by my conversion factor, that should tell me how many moles I have, right? Now before I set this up, I need to make sure I have the right units on the top and the bottom. I have grams here, and I'm converting to moles, so I want moles on top, and I need grams to be on the bottom, so it cancels out. Okay, so I'm going to take this conversion factor and flip it over, right? I have 1 mole per 12.01 grams of carbon, right? So now I just need to take 3.7 times 1 divided by 12.01. My grams will cancel out, and I'll be left with moles. Okay, so this is how I figure out how many moles of carbon I have. So let's do that real quick. So if I have 3.7, divide that by 12.01, I get 0.31 moles of carbon. Okay, so I've converted from grams to moles, right, using my conversion factor. Okay, let's do one more, and then we'll call it good for this lesson. Let's do a molecule. Let's do except I'm going to do moles and then convert to grams. So let's say I have methane. And let's say that I have 2.5 moles of methane. And I want to know what's the mass of this in grams. Okay, well, we're going to use our conversion factor. Well, what's our conversion factor? Recall, it's the molar mass of methane, right? And we talked about briefly earlier, the molar mass is simply adding up the masses that are given on the periodic table, right? So carbon is 12.01, hydrogen is we said it was 1, to be more precise, it's 1.008, and I've got 4 of those. So if I add all of that up, 12.01 plus 4 hydrogen atoms is going to give me 16.042. Okay, so the molar mass, if I have 1 mole of methane, it's going to weigh 16.042 grams, right? I've got 2.5 moles, so I'm going to have 2.5 times that mass, right? And I can see that. So 2.5 moles. My conversion factor is the molar mass. I want moles on the bottom, right? So I can cancel out here. And then I want grams on top. So I know that the molar mass of methane is 16.042 grams per mole. Okay, and so then it just becomes moles canceling out. 2.5 times 16.042 divided by 1 will give me my grams of methane. 2.5 times 16.042, and that gives me 40.105. Okay, so that is conversion factors for converting between different masses of chemicals. Okay, we've talked about the mole and what that number represents, how it connects to grams, and then we've talked about our technique of converting so that we can convert between different units. Okay, so that does it for lesson 2. Go ahead and work on the practice problems, and I will see you in lesson 3.